Okay, thanks, John, and thanks for having me back at Velocity. And in the next 90 minutes, I'm going to cover Linux performance tools. I'm really excited about this tutorial. And what I'm going to help you do is, for any application at all, it doesn't matter if it's a database or if it's a website, any application running on a server, I will show you how to begin analyzing performance, how to step through a sequence of meaningful analysis, and give you an ending point. And that's the hardest part about performance analysis. It's, where do I start? There's so many tools. There's so many metrics. One thing that's great about Linux is it's generally the same Linux that you're running across different parts of your stack. And so once you understand the operating system, you have one way to tackle performance regardless which part of the environment you're looking at, because it's common. It also doesn't matter if you're going to be using one of the monitoring tools. There's lots and lots of great monitoring tools out these days, and they're built upon the same metrics that we use within Linux. And so it's a core skill being able to understand operating systems performance, and this works for any application. I'm going to go through Linux performance tools to show you what can be done and with guidance for how to do it. I have a lot of content in this talk, and a big part of this is giving you exposure so that you know later when the need arises that you can do something. That's more important than knowing how to do it. Just knowing that something is possible, because if you don't know that something is possible and your company really needs you to do this analysis and root cause this issue, you'll never look it up. And so a big part of this tutorial is to sit back and have exposure to all the different things we can do. And you'll remember later, I saw this great tutorial at Velocity, the slides are online, the video's online, I can go and look it up and then study it and learn the parts when you need to. So as part of this tutorial, I'm going to go through objectives, discussion, and some live demos. I work at Netflix. It's an awesome company to work for. We have a massive AWS EC2 cloud. And one of the things that really excites me about Netflix is our culture of freedom and responsibility. And it's also something that it's often discussed on various forums about culture at different companies, especially in the US. And while Netflix is innovating and doing awesome things in terms of the cloud, in terms of our CDN that's doing streaming, I'm also excited about the things we're doing culturally within the company. It makes a lot of sense. It's given me the freedom to go and take on areas of Linux performance that I felt were lacking and improve them and publish tools and work with other great people at Netflix to come up with better tools. So I get excited not just about what we're doing and also the technologies that we're doing, but also the culture as well. So in this tutorial, I'm going to go through methodologies, and that shows you how to take on performance issues, tools, lots of tools, different types of tools, and then two big categories of tools, profiling and tracing. So methodologies. Throughout these slides, and I will be doing some live demos, I've listed objectives. So these can be your takeaways when I'm going through this content, and also when you review this content later. So if you look at the slides online, what are the sort of things I actually want you to pick up? It's really important this is something you get when you are mentored by someone versus just going and doing an internet search on a topic by yourself and drowning in information. When you get mentored by someone, what's really helpful is when they tell you what you don't need to know. And it's because when you search for something or you might open books or you're trying to do your own homework, it can be off-putting, especially when it comes to Linux performance tools, about how much stuff there is. If someone's tutoring you, they can say, don't worry about this and don't worry about that. You need to know a little bit of this. You do need to know this really well. And so that's also a big part of this tutorial is what I've selected to fit into 90 minutes, and also what I've selected as part of objectives, which will help you navigate through the giant field that is Linux performance. So I'm going to, you will be able to recognize the streetlight anti method, perform the workload characterization method, perform the use method, and so on. the first thing I want to start with is my system is slow, and I'd like to do a demonstration. So what I'll do is I'll just switch out of this. I've had this model. I used to do consulting, and I used to teach performance. And I've tried all sorts of different ways to help other people understand how to do this. And one of the most effective ways is to create simulated faults that people go and solve by themselves. I typically do this in, say, a 5-day class, and people can work through them. Now, I've created some of these faults. And what they are is it's a binary program that I can run, and it simulates some issue. A big problem people have when they're learning the performance tools is you try to learn them when your company's on fire. And maybe your boss is yelling at you and your customers are unhappy. And that's when you're actually trying to learn all these tools. I know when people learn to ski, some people say you go to the black diamond runs, and if you make it to the bottom of the run without dying, then you've learned how to ski. I mean, it works for some people, but for a lot of people, it's helpful to have lessons. And it's helpful to master skills one at a time. And so that's something creating small faults can help you with. I've open sourced these, but the source code is not actually that interesting. It's really helpful for you to write the source yourself. So if you're a Java company, if you're a PHP company, if you're using Node.js, whatever the language is, write a few very short simulated issues and just practice solving them. So that you have the known issue before you point the tools at it. So here's one of those issues that I wrote, lab 002. And let's say the customer says, performance on this system is slow. So I'm unhappy with performance. What tools can we run? So a tool a lot of people like to start with is top. So remember, I'm running this thing. It's called lab 002. I run top. Do I see it on my instance? Nope. I don't see it in the commands. So I guess it's probably not eating CPU. Someone tell me what next tool I can run. iotop. I need to install that. I mean, iotop is great. I tend to like to go down to the tracing interfaces to solve the same problem. I mean, I can run iostat and get something. I should have iotop installed. I can run iostat, get something similar out. Iostat is showing me that the disks are basically idle. Okay, so that's interesting. Someone said netstat. Netstat. I never run it without switches. I have no idea what it does. Netstat minus S. That's more like it. Netstat minus S, and there's lots and lots of metrics. All right, netstat minus I. Double S dash S? Oh, you want socket stat, fine. Socket stat, all right. What other cool tools can I run? Remember, the issue is the system's running slow. I've just run top, I didn't see anything. I've run iostat, I didn't see anything. What's that, sorry? dstat. Another tool, I guess you'll discover which tools I don't run by which tools are not installed. So it turns out, I mean, dstat's fine, but like I tend to get that information from SAR, like SAR minus dev. Like if I want to see what's happening at the interface level, I mean, SAR has a lot of nice things. I know some people prefer dstat, and I'm not going to judge, that's fine. Someone said another command. Which one? vmstat. Vmstat's great. System's pretty idle. Strace. Strace of what? Strace of. Okay. Strace of. No, what am I? Okay. What's that? Check resolvers. I could check resolvers. That would be interesting. I could see if it's slow. I mean, I already debugged that issue when I was setting up because like logging into this system was getting slow, and it's like, I know this is DNS. Like I'm familiar with the 30-second timeouts. Like strace, that's interesting. I don't like using strace normally because it slows things down, but strace shows that we're waiting in accept. Yeah, I mean, True, I mean, it wasn't even showing up in top, so like, that thing I did have to know. Other commands? What's that, sorry?
I would start by asking what do they mean by system is slow?
Yeah. What do they mean by system is slow? Like, quantify it. Like, give me a measurement. Is it latency? Where do I start? Like, reproduce it here at the command line. So this is an interesting issue because the program does nothing. All it does is calls accept and then waits there. I've used this when teaching performance classes, and before students know methodology, people can get stuck on this for hours and hours and hours, looking around, trying to find a starting point. One of the nice things about performance methodologies is you can learn how to exonerate a system and do a methodology in, say, 5 minutes. And then just go back to the customer and say, I've checked system resources, they're good. I don't think the problem's the system. How about you look in your own code? And so that's something that this lab helps teach people to do, because you could spend, I mean, you can chase your tail for hours and hours trying to, like, oh, what are the tools haven't I tried? Let's have a look at those complicated tool diagrams and not find anything. So having a methodology that has an ending point. So it's like, well, I've looked at these things. I've looked at my checklist of things. I'm done. I cannot see an issue with the system. It goes back to the customer is actually pretty helpful. Having another methodology where you're asking the customer to quantify it is also helpful. So narrow down the problem before I start running tools and trying to figure it out that way. So there are dozens of performance tools for Linux, and packages like SystemTap, procps, and so on. Methodologies provide guidance for choosing and using them effectively. They give you the starting point, the process, the ending point. I'll start by talking about methodologies by covering anti-methodologies. It's the lack of a deliberate methodology. The streetlight anti-method is named after a parable about a drunk who's searching for his keys. And he's looking for them under a streetlight at night. And a police officer encounters the drunk and says, what are you doing? And the drunk says, I've lost my keys. And the police officer asks, did you lose them under the streetlight? And the drunk says, no, but that is where the light is best. And this is an anti-method because it's something I do see people tend to do, is let's start running the tools that are familiar to me. Let's run top, and let's run iostat, and let's run dstat. And let's go back to top again because those tools didn't work. And it's kind of muddling around, and sometimes it works, and that's fine, but a lot of the times it's inefficient. Another methodology I've actually called the drunk man anti-method. The streetlight anti-method is an observational methodology. So I'm looking at, I'm using tools to observe the state of the system. The drunk man anti-method is an experimental methodology. So I am changing things at random until the problem goes away. It's actually helpful. I named this a number of years ago. At a prior job, I'd gone home one night and I came back the next morning and my coworkers said they had a performance issue while I was gone, and they didn't contact me, but they fixed it using the drunk man anti-method. And immediately I understood how they came up with these bizarre tunable parameters. And that is, they just guessed until the problem was gone. And so it was actually helpful to give it a name in terms of communication. There's also the blame someone else anti-method. And it's something I've seen in the distant past as well. It seems to always come up with, maybe it's the network. Can you ask the network team if they've got like drop packets or something? Or maybe it's the firewall, or maybe it's the crypto cards, and like that's a separate framework. Ask those guys. And then when you come back to it, it's like, oh no, it's going to be something else. It's going to be a database. Ask them. Actual methodologies I want to go through include the problem statement method, the workload characterization method, and the use method, and so on. The problem statement method, this is not specific to Linux tools, but it's helpful to include as part of this slide deck, because it's really useful. And as someone suggested, when I was working on that issue, you'd ask the customer, can the performance degradation be expressed in terms of latency or runtime? And if you'd ask the customer that, then they would give you a more specific starting point for analysis. And so this is something that actually came from when I was at Sun Microsystems, and the support staff would just check the basics every time a performance ticket was raised. So what makes you think there is a performance issue? Has the system ever performed well? I've had issues in the past where people would file a ticket and say, the performance of my database is terrible, you need to fix it, it's atrocious. And it's like, oh my goodness, what changed? I'm looking around at the system and I can't see anything has changed. The system's always been like this. And of course they tell you later, oh yeah, it's always been like that. Like, I gave you the impression that that this is an emergency and it was burning down. It's been like that for 6 months, no one's fixed it. And so I always remember, ask them, has it ever performed well? Has it been like this for 6 months? And only now you're asking me about it. And what changed recently and other great things. So a checklist, easy to do, solves a bunch of issues just at the ticket level. So if you're logged into Jira or whatever, you can actually solve performance issues there before you go to the command line or before you run any performance tools. The workload characterization method is the first real methodology where I'm using metrics and tools. And that's where I want to see the workload applied to the system, not the resulting performance. A big problem we have when we have issues, and naturally I see this at Netflix, I see this everywhere, is when there's an issue, is it because we just happen to have a massive amount of load right now? Or is the target of the load the servers performing badly? Answering that question can be tricky. Workload characterization, who is causing the load? Why is the load being called? Like the code path, the stack trace, the reason. What is the load? So various characteristics like I/O per second, throughput, type of database query or whatever it is, whether it's reads or writes or metadata, and how has the load changed over time. The workload characterization method does solve a lot of issues because it's, you don't realize it, but someone's run a test by accident against production. They should have pointed at the test servers. Or you've now released House of Cards Season 4, and suddenly there's a massive amount of load. Or maybe you released it early by mistake, and there's a massive amount of load. Workload characterization does solve a lot of things. And it's also something that performance monitoring tools are generally good at doing. And so, like I said, there's lots and lots of performance monitoring tools out there. And when I see them, these are the reasons why I'm using them and the metrics I'm going through. The use method is a different methodology. With this one, you take a functional or block diagram of the system, and then for every resource, check 3 metrics only: utilization, saturation, and errors. What's great about this is, for the hardware of a system, there may only be a dozen different components. You can do this for software systems where you only want, say, a dozen key components in your environment. You may do this for your cloud-wide environment and pick the major components there. You'll end up with only 48 metrics or so that you need to check. Not like running netstat -s and getting a huge page of things, but it narrows down the scope. So narrowing it down is useful. Another thing that's really useful is this encourages you to look where your current tools have not. This poses the questions before the answers. And so often we're using monitoring tools and metrics, we're starting with the answers and then we're trying to figure out the questions that led us there. And so the use method is great at uncovering what you're not looking at. And so you can imagine for a hardware system, I've drawn some hardware components there. So CPUs, like I did run top when we were looking at that exercise. Disks, I did run iostat. Network ports, I did run SAR. I could have run dstat, something else. But there's a whole heap of components I didn't check. I also didn't check a lot of things. I didn't check disk errors. I didn't check what's happening at the I/O bridge and the I/O bus and the expanded interconnect. Any component that's in your data path can hurt performance. Any component in your data path can become saturated, and that's where there's more work than it can perform in a given period of time. And so work queues, and that adds latency. Any component in your data path can error. And so errors are actually great to look at because they're objective, they're easy to interpret. And so that's the use method. Now, that's a hardware picture, but you can draw a picture of your the inner workings of your database, your front-end application, your full stack environment, and do the same process. Go around, I have a cache here, I've got Redis here, I've got Cassandra here, and just try to find these 3 high-level metrics: utilization, saturation, and errors. It's just an exercise for posing the questions, and then you'll discover quite often that there's a lot of things that you aren't monitoring and that you probably should. I've done this exercise in the past for Linux, and I put a checklist online on my homepage. It's really long, and it's actually pretty nasty to get through. It's something I would really like to see performance monitoring companies improve and create a wizard for, and give us these metrics at the click of a button. It's something that we're working on internally at Netflix, where we have multiple open source projects. We have one for cloud-wide monitoring called Atlas, and one for instance monitoring called Netflix. Both of them are open source, and I've been going through with Vector, making sure that we can do as much of the use method as possible from that tool. And it's something it's a good idea. It's just one methodology, and it's not going to solve everything. It just solves a particular class of issues. Another methodology that gets a bit tricky, but I wanted to mention it, is the idea of doing off-CPU analysis. So when there's a number of device-level issues that the use method can find easily. Like, okay, my disks are busy, my network interface is busy, my bus is busy, fine. But there's a lot of much more tricky issues to work on that involve lock contention, or I'm blocked waiting for a conditional variable, or I'm blocked in the network stack for some reason. And there's lots of them. And I might be blocked because I'm doing swapping or anonymous paging. I might be blocked because I got involuntary context switched by the kernel, and I had to wait my turn on the run queue. Off-CPU analysis is nice as it gives you one methodology to attack them all, and that is, let's instrument when my application steps off CPU. This is a lead way into all the different tracing tools that exist. If I can instrument when I step off CPU and why I stepped off CPU, I can attack all of those issues. So it's a really effective methodology for a lot of the more mysterious issues out there. CPU profile method, I just wrote this up as a methodology because it is something I use, and that is take a CPU profile, and then here I've visualized it as a flame graph, which I'll get into in a moment. And then you just understand all the software that's running on CPU that's more than, say, 1%. A big problem when you're analyzing by the way, flame graphs exist for all sorts of languages these days and things. A big problem we have with performance is there's so much stuff. And even if you narrow it down to like one database like Cassandra or MySQL, and you look at what can be turned on and all of the features, there's heaps of things. And you can run their status tools and get all the metrics out. It's very laborious and time-consuming. Quite often, these complicated databases and applications, they have all these features that aren't even turned on. So don't worry about looking at the cache activity at that level, or the asynchronous log writer tasks, or the persistency fork exec model, or whatever. That stuff's not turned on. Like, we don't have that turned on in the environment. And so it just becomes a complicated procedure when you're looking at the database and you're trying to understand all of it. If you profile what's running on CPU, the nice thing about it is it reveals what's turned on. You can't run without stepping on CPU. I've caught you. I know you're running. And that can help narrow down what parts of my database actually matter. They should be showing up. They may be showing up a small amount because they're not as CPU heavy as other parts, but it's just a way to narrow down what to study. RTFM method, which I wanted to write up as a methodology just to make sure we're good at this, and that is, how do you understand performance tools or metrics? And so remember to look at, there's man pages, books. O'Reilly has lots of good books, of course. Web search, ask your co-workers, prior talks and slides. You might have support services for understanding things. But 7 and 8 are really important. We live in the age where we kind of expect things to be open source. And so I spend a lot of my time, well, not a lot of my time, I spend enough time reading the Linux kernel source code or the source code to the Java JVM or whatever, just to really understand what the metrics mean. And also doing experimentation. And that is where I can't really get my head around this metric, but what if I wrote a little program that exhibited the problem? It should light up the metric. So those are two really useful ways to understand performance tools and metrics. Reading through the source code and also doing little experiments. So that's several methodologies. The next section is tools. And I want to show how you can do the use method for resource utilization, workload characterization, CPU profile method. A big part of this, however, is exposure to all the different observability tools so that you know what can be done. I am at the command line, and you may say, I don't care about the command line because I look at my servers from higher-end performance monitoring tools. Often they're getting the metrics from the same place, in proc and sys from the kernel. And so if you understand the standard tools like vmstat and iostat and top, you will understand many of the performance monitoring tools because there's so much overlap. It's like I've seen those metrics before. I know where they come from. I've categorized the performance tools into 4 types: observability, benchmarking tuning, and static performance tuning. Observability tools are generally safe, so you can watch the activity. Benchmarking tools, it's useful to do, so I can do experiments or load tests and see how the system responds. Tuning is where I'm changing things. And static performance tuning, I'll explain when we get to it. So the first one is observability tools. And how do you measure all of these components? It's really helpful if you have an environment, you don't have a functional diagram, to start by drawing it, because it then gives you an effective visual checklist of, okay, what do I need to at least understand? What's in my data path? I'll go through some of these quickly. It's more for exposure. So basic observability tools. There's lots of different ways you can dig out the CPU load, I shouldn't say CPU, system load averages. Used to be CPU. One of the ways is just the uptime command. You see it in top. You'll see this even graphed by performance monitoring tools. They are 3 numbers which represent the 1, 5, and 15-minute load averages. These numbers are actually exponentially damped moving sums, and so they aren't quite 1, 5, and 15 minutes. In fact, at the 1-minute mark, it's only counted something like 61% of the value is incorporated into that metric. So they're damped. Giving you 3 numbers helps give you an idea of how the system's changing. And so this is ancient. This comes from at least 10x or CTSS back in the 1960s, before Unix, the notion of having load averages. And also, in the days of mostly text displays without graphs. And so having 3 numbers is a simple text way of showing the passage of time, or what's happening over time. If the 1-minute average is higher than the 5 and higher than the 15, you know things are getting busier now. If the 1 minute is lower, you know things are getting more idle. The load average is supposed to represent how much load is applied to the system. It used to be, and I explain this because if you try and read other documentation, it can get confusing. It used to just be about CPUs, and it was just about how many CPU processes or tasks are either running on CPU right now or are queued waiting their turn to run. And because of that, if your load average was greater than the number of CPUs you had, so if you had a load average of 5 and you're on a 4 CPU system, you generally have more CPU work than the CPUs can dispatch. If your load average was 2 on a 4 CPU system, you should have headroom, although it can vary from second to second. Linux incorporated the uninterruptible disk I/O state into load averages, which really confused things and complicated things. So now load incorporates more than just CPU load. I guess I understand the rationality. Rationality is it should include if tasks are blocked on disk or other resources, not just CPUs. It has made interpreting these even more difficult. You shouldn't really spend more than 5 minutes looking at load averages anyway. So I just look at them for, 5 seconds. Just look at them for 5 seconds just to see if the system's totally idle and it's 0.01, or if the system's generally doing a lot of load, you have to use other tools to understand it. Things like top or htop. Top has a great system-wide summary at the top, and then we've got the per process or per task information. I've highlighted a couple of columns like %CPU and the command. It's a great system-wide summary, solved countless issues. CPU is summed across all CPUs, that's why Java can be at 417%. A problem with most implementations of top is that they sample when they update the screen, but you can have short-lived processes that begin and finish in between the screen updates. And so your load average can be really high, but your CPU column can be mostly 0. And you can't find, it's like, why is my load average, or you can actually see the CPU summaries, the user system time, nice, idle, wait IO, and so on. You can see that the CPUs are busy doing work, but you can't identify the processes responsible. And one reason is you have short-lived processes that are missing sampling. ATOP actually solves that. ATOP does use the event interface. Another reason maybe it can be kernel task, kernel work that you can see from the summaries as well. Top can actually take some CPU time to read proc. I mean, these days not so much, but on older systems, if everyone jumped on an issue and ran top at the same time, you'd see top as the first few commands. And now you had 2 issues. It's like the issue we were debugging, and now we have 7 sysadmins running top. So let's all stop, let's one person run top, and then there's htop. htop has some visualizations, is more customizable. PS, much more basic tool at the command line. And I've got actually the ASCII art forest version of PS where it shows the parent-child process relationship. PS is nice in that you can dig out a lot more columns than you normally get out of top, although you should be able to configure these out of htop. For some reason, I might need to shell script some ad hoc things and get it out of PS. So the kernel does contain lots and lots of interesting metrics beyond what you normally see in the limited display of top. vmstat, virtual memory statistics and more. vmstat has existed for a while, came from the BSDs, and it gives you a system-wide summary just in one line. So we've got I've highlighted the columns my eyes tend to focus on. We've got R for the run queue length. A number there indicates CPUs have tasks running and also tasks that can be runnable, so they're not actually running, but they're waiting their turn. Memory broken up into free, buffer, and then the page cache. And then the last few columns are pretty interesting. So the CPU summary is broken down into user time, what my applications are doing in, say, the JVM runtime or the Node.js runtime, and then system time, which is what the kernel's doing. My application can be doing system calls, or it can be processing interrupts or other kernel tasks. iostat came from the AT&T Unix. Says, I really like, vmstat's been cleaned up over the years. These days it kind of makes sense. iostat has always had a really nice design. Linux has improved it. I like it because I get to apply multiple methodologies to the iostat output. The only thing I don't like is that it's more than 80 characters wide, which is a sin when it comes to Unix, and breaks my slides as well as books. But that's okay. These days we have very wide terminals. Workload characterization. So I can apply that methodology and say reads per second, writes per second, throughput, reads and writes, and just see if the workload applied to the disks is insane. So I know I've got a disks issue, like, am I doing 10,000 IOPS to some spinning Rust? That might tell me that my application is just sending too much load. And that can be a big clue before I start understanding the resulting performance. Resulting performance is great as well. So we've got average queue size, average wait in milliseconds, which is the overall time you're on average waiting for the block device or disk I/O. And then service time, which is calculated to remove queuing. And percent utilization, the last column, is really a percent busy. So during an interval, how many milliseconds out of a second was that device doing work? Utilization I'm using in the use method, utilization, saturation, and errors. So I get to use that guy. I get to use the latencies if I'm doing latency analysis, and of course workload characterization. Nice tool. I've recommended this to people in the past when they've asked me, they're instrumenting a new subsystem in an operating system, and they've said, what statistics should I provide? Copy iostat. So copy these because I get to do a whole heap of methodologies straight off these. It's a nice set. If you have no idea how to instrument something, it might be a new application you're writing, but you can understand, like, give me a high-level breakdown of the workload applied. It might be client logins and client activity broken down into different dimensions. Then give me some high-level idea of the resulting performance, including how often the application was busy. It would only be perfect if it had another column for errors. So I can do the use method fully. MPstat I've included as another basic tool. MPstat for multiprocessor statistics. I'm generally running this because I want to look at the balance, CPU balance, see if there's hot CPUs, which can be an issue of an application. These free numbers appear in other tools as well, so they're in top. So I can see my block device IO cache and the virtual page cache. So let's use some of these tools now for another issue. So I'm going to run lab 005 this time. And this time the customer has said, my application latency is much higher. Can you debug it? We can go through the workload, the problem statement method is really the first place to start. And so you ask the customer, what makes you think there is an issue? And they say, I'm measuring average latency, mean latency, and that has gone up. My latency distribution has gone up. And that's affecting clients. And you go through the problem statement method, and there seems to be a legitimate issue. The use method is a nice thing to give us a starting point and an ending point. I like to do the use method. It takes like 5 minutes. There's a lot of metrics I'm not looking at because there's no easy tools to get down into the buses yet. That's something we should fix. But at least I can go through the basics for the use method quickly and then go back to the customer. So for the use method, I just want to know utilization, saturation, and errors, if they're readily available, for the hardware resources. So let's start with top. So I've got my CPU summary at the top. It's the third line. And we've got 4% user time, 38% system time. So the kernel's doing a bunch of stuff. That's going to be interesting to debug, 38%. But we do have a lot of idle time and wait I/O. So it doesn't look like we've maxed out the CPUs. And so I'm not sure that there's evidence of saturation. There's my lab 005. It's eating, what, 12% CPU? So I don't have 100% CPU utilization. I can see it here as well. So I have moderate CPU, especially system time, but I've got plenty of idle time and also wait I/O. Just a little bit over here in the R column. I can also break it down. Let's see if it's not actually a multiprocessor system. I'm just running a virtual machine. But I'll check that as well, just to see if I'm maxing out a single CPU. CPUs look OK. It would be interesting to understand that, but we're not maxed out. We still have idle. Memory, looks like there's plenty. So in terms of utilization and saturation, we're not swapping aggressively. We're not fully utilized in terms of memory. Let's do disk next. Well, with disks, we are pretty busy. So utilization is now, for the disks, it's 78%. And I'm just going through the use method. I'm looking for those metrics to start with. I can see the workload applied. We're doing 4,000 write IOPS and 19 megabytes a second. This is a slow machine, slow virtual machine. The actual response time is OK, but it's a lot of load, and the disks are getting busy. So that's probably a bigger clue than CPUs. when you max out CPUs, systems can generally, Unix-like systems can generally be graceful about it, time-sharing systems, because the kernel understands priority. It can rip threads off CPU very quickly if it needs to and run other threads. The same is not so true of disks. When you max out disks, or rotational disks, it's hard to send I/O with higher priority, dispatch it to the heads, disk heads, if they're already in flight doing something else. A little bit different nowadays with SSDs, but you can get to the point where you've queued a lot of work on the physical device, and the kernel has less control about who gets to run in their priorities. And so generally with disks, you start to see, it will vary, but you start to see performance issues beyond 60% utilization, definitely beyond 80% utilization. So disks is most likely. I could stop there and say, well, disks look really busy. You should check out, why is your application doing more writes to the file system or writes to the disks? But for the use method, I do want to finish them all. So I want to check, lots of different ways you can do this. I want to check network I/O as well. It's my other key device. And that looks idle. And that's it. So I'm done. I'm done with the use method. I've checked 4 major resource types. I go back to the customer and I say, disks look pretty busy. CPU looks moderately busy in system time. It could be in kernel time, but it may be related to this. It may be related to the disks. That may be enough information for the customer to say, oh, that's right, we changed a property setting in the database. So now it's flushing the writes all the time. We'll go revert that change. And so I've quickly reached an ending point, give back to the customer, and then continue on. Without an ending point, I may spend way too much time drilling into this, and I'd be profiling the CPU time next. Let's do distributions of disk I/O latency, and so on and so on and so on, which is all very helpful, but maybe overkill. So I used some of the basic commands. That's a system diagram with the basic commands illustrated, and you can see there's a lot of blanks. So I haven't covered a lot yet. But still, we can get to do some methodologies just from those. Intermediate. So strace, tcpdump, netstat, nixstat, and I'll go through some of these quickly. strace is a system call tracer. Here I've run it with options so I can see timestamps. I should have changed that slide. It can be very, originally used that at LinuxCon, now it's Velocity. It's originally was written using ptrace, and most implementations are still using ptrace. There has been some work on Linux to come up with ftrace, which uses the more efficient perf events framework to do a version of strace. But most implementations of strace right now are still using ptrace, and it can slow the target down by over 100-fold. It's something that we want to be very cautious about using. Nice to see the system calls that are happening because you get to understand the workload that's applied to the kernel, but the way strace operates is violent. It sets up breakpoints. The way it currently works, like I don't need to prefix this because there is work to fix it in terms of Linux perf events and the trace subcommand. But the way it currently works, and probably will work for a number of, many, many months yet to come, is it blocks the target when it begins doing a syscall and then unfreezes the target when it continues. And so that context switching and freezing and unfreezing can slow down applications a lot. I'm really careful about running strace in production. tcpdump is something similar, but instead of doing a trace of the system calls, we're doing a trace of the packets. And there is a whole universe of analysis and GUIs that people like to use for digging through network packet traces. Hugely useful. You can go through packet sequences with timestamps and look at what's happening on the wire. Generally, you're dumping to a trace file and then analyzing it afterwards. I like to go into the kernel and use more kernel level summaries for answering some of those issues, because it's getting more and more difficult to use tcpdump in faster environments. So if you've got a 10 gigabit interface, a 10 gigabit Ethernet, and you're pushing over a gigabyte a second of data, and the performance issue I want you to work on is once every 30 minutes there's a latency outlier. Doing 30 minutes of like a gigabyte of data to a TCP dump, now you've created a massive performance issue, and that is your TCP dump file is terabytes, and you have to, are you going to analyze it on the server? Are you going to SCP it down to your laptop? That's going to take hours and hours and hours. So it's getting harder and harder and harder to TCP dump is not scaling in modern environments, so it has a scalability issue. It's still going to be used. There's still going to be plenty of use cases where it's great and it helps you solve issues, but just be aware that we have to build other techniques, and that's what we're doing with in-kernel tracing and summaries in order to answer some of the problems we used to just run TCP dump for. Netstat is a multi-tool, lots of subcommands like netstat -s I ran earlier, and to understand all sorts of things that are happening at the TCP level. I wrote nixstat a long time ago, it was ported to Linux, just so that I could go through. You can see what I based nixstat on. It's based on iostat. So I've got the workload applied and then the resulting performance, or utilization and saturation. And so I can also do the use method. I think I've seen it in some repositories, so you can just add it to systems. PIDstat is one of my favorites, intermediate tool. PIDstat -t will show per thread breakdowns, so I can see user time and system time for each process. And that gives you a clue of what type of analysis you want to do. If it's mostly user time, you know it's in the application code. If it's mostly system time, you might be looking at system calls, what device, iostat for device usage, and so on. PIDstat -d gives you an idea of the block device I/O a process is doing. And so there happens to be bean counters in the kernel for that, so it's nice. Swap on I've included in my intermediate list, just to check swap device usage if you've exhausted memory. If you have swap enabled, a lot of systems these days don't. LSOF, it's more of a debug tool, but there are some performance issues that it can help solve. And so you have too many file descriptors that are open, and you may be running into limits there. It also helps you just understand an environment by seeing who's connected to who. So I'm running LSOF to see that this application on this port is connected to this other host on that port. There's SAR, the System Activity Reporter. The Linux version of SAR is actually really nice. So it has two modes. It has archive mode, so you can cron tab it and it will gather, say, 10-minute interval summaries, or you can run it live. And so here I've run it with TCP stats and error TCP and then the network interface device stats. And so I can look at, I actually ran that earlier, the dev information, but active and passive is TCP. So active is outbound connections, passive is inbound connections, and I've got retransmits as well. SAR is actually great, and it's also pretty well designed. So the units are on the columns, there's a nice naming scheme, and the selection is also pretty good. In fact, it's so good I've come up with a diagram to show you the options for SAR, so you can see what they're exposing, and that's not too bad. It would be really nice if there was a system call interface, if there was just at least a count of system calls per second in SAR. Plus you could like split it out into forks and execs and reads and writes, but it's actually pretty good. So you can solve a lot of issues with SAR alone. dstat is something, I could do a similar diagram for dstat, I can do a similar diagram for collectl. They're all tools in a similar space. SAR even has fan statistics if they're supported. So you may be using one of these measure all tools. The tool itself is not that important. It's just important to have a way to measure everything. And so in our cloud environments, I mentioned earlier at Netflix, we develop Atlas and Vector for cloud-wide monitoring and instance-level monitoring. And so it's important for us to have a way to get to these metrics. And when you have functional diagrams like this, you may, one of your takeaways from this talk is to print out a slide like this and to say, using the tool set that we have and all the monitoring tools we typically run with, how do we monitor all of these components? And so just to, you can, I've put a scorecard there so you can score your current environment. So as another demo, so an app is taking forever. Let's have a look at this one. The customer says, my application is taking forever to run. Now it's really slow. It's like, okay, fine. Let's have a look. Covered a bunch of new tools. Let me just start with the system-wide summary, vmstat 1. I'll start with the use method. I see I've got a lot of user time and system time. I'll see the same thing in npstat. I can now run pidstat. Lab 003. Lots of user time and lots of system time. So system time, is it because it's talking to the disks? The answer is no. Completing the use method. Are we talking to the network devices? No. So it's like, well, what is that system time? What is that system time going to be? So I can see I've got a chunk of system time, but the disks are idle and my network interface is idle. Am I swapping? Which I'd also check with the use method. No, I don't see swapping. What else can I run? What command can I run to figure out this system time that I just covered as part of the intermediate? strace. Even though I said I don't like strace because strace slows things down, there are better tools, but I haven't covered them yet. Sometimes getting the job done can be useful, even if it means briefly slowing things down. I can run strace. I don't want to leave this running because it'll fill the screen and slow down the application. So I may just pick off the first 100 entries. I wish strace had an option for this. If you want to, please edit strace and add like -c or like a count of, like with tcpdump, so you can be like exit after capturing this many. Even better if you change it so it doesn't use ptrace and uses perf events so that the performance overhead is really small. But let's just gather 100. So you can see it's really busy, actually. Now put a timestamp at the front. And it's calling read on file descriptor 3. And how many bytes is it requesting? It's actually requesting 0 bytes. The application is stuck in a loop requesting 0 bytes over and over and over. I've seen this in production. Not at my current employer, but I've seen this in the past, and it's where the application developer has used a variable for the size of bytes to read, and due to a logic bug, that variable is now set to 0. And so they're in a loop trying to read a database file 0 bytes at a time. That loop's never going to finish. So, but I just wanted to go through this as a methodology. Like, even though I don't like strace and it may have slowed it down a lot, I answered the question for the customer. And what type of answer is this? It's workload characterization. It's just the workload that's applied is dumb. I'm reading 0 bytes at a time. Quite often I've done this into reading 1 byte at a time, or 16 bytes, or something small. And you say, well, go to 8 kilobytes, go to 128 kilobytes. That will load it much more quickly. So just workload characterization, this time of system calls. I should mention strace on Linux has in the past sometimes frozen applications. So you've tried to run strace, and then you're done, you Control-C, and it's left the application in a kind of stuck state. So, so do use with caution. Do test it out in the lab before using in production. But always be cautious with strace. The thing is hugely violent.